Jai Hind everyone. Myself Dr. Sharma from Ajay Kumar Garg Engineering College. My subject is Engineering Physics and the subject code of my subject in odd semester is KS101T and in even semester subject code is KS201T. The topic which I have taken for today's discussion, that topic is laser, and under this topic the different subtopics which I am going to discuss are the basic processes which are involved in laser, and under this we are going to discuss about stimulated absorption, spontaneous emission, stimulated emission. After this we will discuss that what is the principle of laser action, means how the light will get amplified in case of laser. After this we will discuss that what is the significance of metastable states in a laser system, and finally we will discuss that what are the essential components of a laser system. So these are the topics for today's discussion. Now the first point which I would like to discuss here, that what is the meaning of laser. When I am saying laser, then it is a combination of 5 words, and these 5 letters. These 5 letters are LASER, and the meaning of this entire topic that is hidden under these 5 letters. In this laser, L stands for light, A stands for amplification, S stands for stimulated, E stands for emission, and R stands for radiation. So the complete meaning of laser is light amplification by stimulated emission of radiation. So that is the complete meaning of laser. So what I had told you, laser stands for light amplification, and that amplification will take place through a process, and that process is stimulated emission. So that is a complete abbreviation of this this laser. And now we will try to understand all these all the subtopics like stimulated absorption, stimulated emission, spontaneous emission, principle of laser action, and main components of laser through this stimulated emission. So the entire meaning is hidden under these 5 letters. In case of laser, we are getting amplified laser beam, and in that amplified laser beam, basically the light is obtained in the laser light is mainly obtained in 3 main regions of electromagnetic spectrum, and those 3 regions are ultraviolet region, IR region, and visible region. So mostly the laser which we have in the market, they operate in these 3 regions of electromagnetic spectrum. So either the laser which you are having that will operate in UV range, IR range, or in visible range. So these are the 3 regions. Mostly laser operates in 3 main regions of electromagnetic spectrum. Now let's discuss the properties, the characteristics because of which laser light is superior as compared to ordinary light sources. So as you can see in this picture, in the first one you can see you have an ordinary light source, and in the second one a laser source is shown. So as you can see here, when you have an ordinary light source, it will give you light in all possible directions. Whereas in case of laser light, the light is highly directional, means the light is only confined in a single direction. So because of this reason, the laser light can be used in those applications where you want to focus laser beam, or where you want to focus light on a certain point or certain region. So some features or characteristics are there which are making laser light very much popular as compared to ordinary light sources. So let's discuss those major features or major characteristics of laser light. So as I have mentioned here, there are 4 characteristics which are making laser light very popular, very much superior as compared to ordinary light sources. The first and the most important one is coherence. So as you know, the meaning of coherence is the light rays which are coming from a coherent source, those light rays either they have 0 phase difference or constant phase difference. That is the meaning of coherence. So the meaning of coherence in case of laser is that laser light is highly coherent in nature as compared to other ordinary light sources. So laser light that can maintain crust to crust or and trough to trough correspondence, the extent to which the coherence can be maintained, that is much higher than ordinary light sources. The second one is laser light is highly directional in nature. As shown in the previous slide, that laser light is confined in a single direction. It is highly directional as compared to ordinary light sources. So this is also a very important feature because of which laser light is used in many applications. Then the next one is laser light is highly monochromatic in nature. I'm not saying strictly monochromatic, because even for laser light, there is a spread of wavelengths. Means the main wavelength which you are getting from a laser source, around that main wavelength, you are getting some more lines or some more wavelengths. But that spread of wavelengths, that is very small in case of laser, whereas in case of ordinary light sources, that spread is very large. So what I am trying to say here, laser light is highly monochromatic in nature. The next one is laser light is having a very high intensity. Its brightness is much higher than ordinary light sources. So what is the meaning of this particular term here? As you all know from your previous classes, that intensity of any light source, that is given by this particular formula. Intensity is basically power per unit area. So when I'm saying power per unit area, in case of laser, as you have seen in the previous slide, that laser light is confined in a very small region. So when the region in which laser light is confined, when that region is small, it means area is very small. So as you can see here, this area is in denominator. So smaller the area, greater will be the intensity. So since in case of intensity as well as in case of brightness, we are getting this area in denominator. So because of that reason, you can say that intensity as well as brightness of laser light or laser sources is much higher than ordinary light sources. So these are the four main features because of which we are discussing about laser here, because of which laser light is very much popular for different applications and different fields. So as you can see in this slide, the first picture is representing the highly coherent behavior of laser light, and the second one is showing the high intensity or brightness of laser light. As you can see, the light rays which are coming from a laser source, they can maintain crest to crest and trough to trough correspondence. That is the reason this laser light is highly coherent in nature. And in the second case, from this laser source, we are getting light, and that laser light will get focused on a very small region here, on a very small spot here. So because of that reason, area is very small. So smaller the area, intensity will be greater, brightness will be greater. So these two represents the coherence and in high intensity and high brightness of laser light. Now let's discuss about our three main processes which are involved in laser. So the first one and the first step in order to understand laser action or laser systems is stimulated absorption. So before going into detail of these processes, what I'm going to assume here, I'm going to take an assembly of atoms or electrons or ions or molecules. So suppose you have N0 atoms. You can imagine any number in your head, like there are 100 atoms or 100 electrons, ions or molecules. And suppose they are distributed, they are present only in two states. So if there are only two states, 1 and 2, and N0 atoms are there, N0 electrons, ions or molecules are there, then in that case, 1, which is the lower energy state, which is also known as ground state, that will be most stable energy state. According to Maxwell-Boltzmann distribution, the number or the population of electrons, atoms, ions, molecule in a particular system, that population depends upon the energy. So if you have two states, 1 and 2, state 1 is the ground state or lower energy state, and state 2 is a high energy level. Since 1 is the lower energy level, and 2 is the excited state, and according to Maxwell-Boltzmann distribution, we have this expression for population of any energy state. So this formula is representing the population. So as you can see here, there is an exponential decay factor which will represent the population of any state. So if you have two states, one with lesser energy, two with greater energy. So it is very much clear from this mathematical expression that smaller this E, smaller the value of E, greater will be the population, because with the increase in this E, when the energy of a state will increase, suppose you have a high energy level, then this exponential decay, this exponential factor will take a smaller value. So, greater the energy, lesser will be the population. Smaller the energy, greater will be the population. It means the lower energy levels are more populated. So, what you have an assembly of atoms. In that assembly of atoms or electrons or ions or molecules, there are two states. And the total population that is distributed in these two states means those electrons, they are either present in one or two. So, according to this, the state 1, which is the ground state, that will be most populated state. It means most of the electrons, they will be present in ground state, most of the population will be in ground state, and only few will be there in excited state. So whatever I have explained, that can be understood with the help of this diagram. As you can see here, 1 is representing the ground state, and that state number 1 is having energy E1. 2 is representing excited state, and let E2 is the energy of that particular state. These green circles which you can see here, these circles are representing the population of state 1, and lesser the energy, greater is the population. And since 2 is an excited state, so as you all know, it is the rule of our nature that everything tries to remain in a stable state. So since 1 is the ground state, most stable state, electrons can stay here for infinitely long time. So this one is most populated state. So you can say ideally only few or no electrons are there in excited state. So you can see here this state number 1 is most populated. When you will provide energy to this assembly of atoms, so you have this particular combination, you have this distribution of atoms in these two states. Now what you are doing, you are supplying energy to this assembly. So when you will supply energy to this assembly, then there are two transitions which are possible. Either a transition from 1 to 2 or a transition from 2 to 1. Means either these electrons will move from 1 to 2 or they can come down from 2 to 1. These are the two possibilities. You know that when these electrons are in ground state, they require some energy to move from ground to excited because their energy is lesser in ground state. So if these electrons, they want to move from 1 to 2, they require this extra energy, that is E2 minus E1. So suppose from an external agency, you are providing photons of energy E2 minus E1. These photons can be absorbed by these electrons of ground state, and after absorption, there can be a transition from state number 1 to 2. So when this transition will take place, this transition is not a natural process. This transition requires a stimulation. This transition requires an external trigger. This transition requires an external photon. Only after absorbing that photon, a transition is possible from state number 1 to 2. And during this transition, since energy is absorbed, these photons of energy E2 minus E1, these photons are absorbed, and only after that absorption, this transition will take place. So that is the reason this particular process, this is known as absorption process. And since this process requires an external trigger or stimulation, that is the reason the complete word for this process is stimulated absorption. So that the stimulated absorption, that is the first transition which is indirectly or participating in light amplification in laser. So what you have N0 atoms or electrons or ions or molecules distributed in two states. From Maxwell-Boltzmann distribution, population of ground state will be maximum and only few will be there in excited state. When you are providing external energy, transition will take place either from 1 to 2 or from 2 to 1. Right now we are discussing a transition from 1 to 2, but you have to understand here, transition from 1 to 2 is not a spontaneous or a natural process. For this transition, you require this external trigger. So that is the reason this is stimulated process, and since energy is absorbed, that is the reason this is stimulated absorption. So this is your first process, stimulated absorption. So whatever I have mentioned through that diagram, all these points are discussed in this slide. So photons of energy h nu are absorbed, and I hope everyone is clear that this h is representing Planck's constant here. So what is required? Photons are required, and how much energy is required for those photons? Energy equal to the energy difference between 2 and 1. So these photons are of energy h nu, or you can say E2 minus E1. So for stimulated absorption, you require these photons. Now the next process, which is participating in light amplification in laser, indirectly. Directly stimulated emission is participating, but without stimulated absorption, which I have already discussed, and this one, spontaneous emission. The third one, stimulated emission, is not possible. So it is very much important to understand spontaneous emission also. So what you have N0 atoms, and those N0, that population is distributed in two states, 1 and 2. And as I have already mentioned, 1 is the most populated state and only few electrons are there in excited state. Now the second one, the second case, you have these excited electrons in state number 2. When I am saying excited state itself representing highly unstable state. Highly unstable means the lifetime of this particular state is very, very small. These electrons, they can stay in that particular state only for a short duration, which is roughly of the order of 10 raised to power minus 8 to 10 raised to power minus 9 seconds. That is the meaning of unstable or excited state. When I am saying ground state or stable energy state, then for infinitely long time, electrons can stay in that particular state. That is for your ground state. But when I am saying excited state, it means that is a short-lived state. So in case of spontaneous emission, what is happening here? You have few excited electrons here with a very small lifetime. So once the lifetime of these electrons will be over, then these electrons, after completing their lifetime, they tries to achieve a more stable energy state. Means they try to come down to this lower energy level. But you know, when these electrons are there in excited state, their energy is much higher than the energy of ground state. Their energy is E2. But if this transition will take place, then during that transition, those electrons, they have to release their extra energy. They have to emit their extra energy. So after completing their lifetime in excited state, these electrons will automatically come down to ground state. And when they are coming down, their energy in ground state should be E1, but their energy is E2. It means they have to emit their extra energy, which is equal to energy difference between these two in terms of a photon. So what you are getting here, a photon is emitted, and that photon is of energy equals to h nu, which is actually equal to energy difference between the two states. So what you have excited electrons with very small lifetime in state number 2. Once that lifetime will be over, these electrons will automatically, spontaneously or naturally, they are coming down to state number 1. So when this natural transition will take place, then these electrons, they have to release their extra energy. So that energy is emitted, and that energy is emitted in terms of photons. So this process, since no external trigger, no stimulation is required, so this is a natural or a spontaneous process. And since photons are emitted, so this is emission process. So the complete word to describe this process is spontaneous emission. But one point you have to remember here, that different electrons which are there in state number 2, they are going to complete their lifetime at different times. Means, suppose at a particular instant of time, 10 electrons are coming down and they are releasing 10 photons. Then after a particular duration, some more electrons are coming down. It means the photons which are emitted due to transition from 2 to 1 in spontaneous emission, those photons are moving in random directions. They are not having fixed phase relationship. Means the transition because of spontaneous emission is not coherent in nature. So all the ordinary light sources which we are having, those ordinary light sources, they are giving us light through the spontaneous emission process. Right? I hope you are getting my point. In case of spontaneous emission, the photons which are emitted, those photons, they are not in same direction. They are not having a fixed phase relationship. So light is not coherent. Light is incoherent, which is obtained due to spontaneous emission. And one more point you have to remember, that all the ordinary light sources are giving you light through the spontaneous emission process. Right? So this is your spontaneous emission. And one more point which is important here, that photons of exactly same energy, E2 minus E1, are emitted during this transition. Now the third one. So this is all about spontaneous emission, which I have already explained here. Now the third one, or the third process, which is basically participating in light amplification, which is actually the phase of your light amplification in laser. So stimulated emission. But as I have already mentioned, that stimulated emission is incomplete, not possible without stimulated absorption and spontaneous emission. So how those two processes are equally participating, that you have to understand now. So let's first try to understand what is stimulated emission. So in order to understand this, again we are having same combination, N naught electrons distributed in two states. One is most populated, only few electrons are there in excited state with a higher energy. And you also know that state number 2 is highly unstable energy state with a very small lifetime of approximately 10 raised to power minus 8 seconds. Now as you can see here, before the completion of lifetime of this excited energy level, what I am trying to say here, suppose you have an electron in excited state. You know, after 10 raised to power minus 8 seconds, automatically that electron will come down to ground state and it will release extra energy in the form of photon. But that will be your spontaneous process. Now in case of stimulated emission, what is happening? You have electron in excited state, but it is still intact, it is still there in its high energy level. So when it is present in high energy level, suppose a photon is coming. So this particular photon is coming, and that photon of energy E2 minus E1, it is interacting with this excited state electron. So when this interaction between this photon, this electromagnetic field of this photon and this electron, then this photon is acting like a trigger, this photon is acting like a catalyst, and because of that interaction, this electron, before completing its lifetime in high energy level, it is coming down to ground state. What is happening? You have this electron in excited state, but it is still there, means it has not completed its lifetime. Before the completion of its lifetime, this photon is coming and the electromagnetic field of this photon is interacting with this excited electron of state number 2. And because of this interaction, what is triggered? A transition which will take place after 10 raised to power minus 8 seconds. That transition is triggered before that time from 2 to 1. And when the transition from 2 to 1 will take place, you know, electrons, they have to release their extra energy, which is E2 minus E1. So now exactly what is happening? This photon is there. It is triggering a transition from 2 to 1 before 10 raised to power minus 8 second. Means this transition is not natural process now. It is a stimulated process. And since during this process, photon is emitted, so it is a emission process. So the complete word to complete term to describe this process is stimulated emission. So what you have? You have a photon. That photon is acting as a triggering photon. This photon is forcefully sending electrons of high energy state to ground state. And because of that transition, photons of extra energy that will be emitted. So now you have two photons. One, which was the triggering photon, and the second photon is the photon which is emitted due to transition from 2 to 1. Means this particular photon is of energy E2 minus E1, and the photon which is emitted due to the transition from 2 to 1, that is also same energy E2 minus E1. So instead of one photon which was initially provided, you have two new photons. So one photon is converted into two. Then these two photons, they can trigger two more downward transitions here. And if two more downward transitions will take place, then you will get two new photons. It means two photons then will convert into four photons. Means these photons will get multiplied. And all these photons, they are moving in same direction. They are having a fixed phase relationship. So they are highly coherent in nature. So all these four photons, they are moving in a certain direction. They have same energy. So photons will get multiplied. 1 will convert into 2, 2 will convert into 4, 4 will convert into 8, and this multiplication will go on. And finally, you will get an amplified laser beam where you will get an avalanche of photons. And that avalanche of photons is basically your laser beam. So this is your stimulated emission, which is actually amplifying light in laser. But you have to understand one thing here, that this photon, this is acting like a catalyst. As you all know, what is the role of a catalyst in a chemical reaction? If you have a catalyst in a particular chemical reaction, then basically the role of that catalyst is to enhance or is to increase the rate of reaction. The same role is played by this photon. This photon is not actually participating in light amplification. This photon is triggering the transition from 2 to 1. Actually, this transition can take place spontaneously after 10 raised to power minus 8 second. But before 10 raised to power minus 8 second, this photon can trigger that transition from 2 to 1. It is acting like a catalyst. And you know, in any chemical reaction, if you have a catalyst, then finally you will get the catalyst in same form. So this photon will remain in the same form. It will only trigger the transition from 2 to 1. So one photon converted into 2, 2 converted into 4 photon, and then you will get amplified laser beam. So as I have mentioned 2 to 3 times, that this stimulated emission that cannot take place without stimulated absorption and spontaneous emission. So that I will explain through the principle of laser action. So these are the three processes. So whatever I mentioned about stimulated emission, all those points are covered over in this slide, that you require a triggering photon of energy E2 minus E1, and that triggering photon is responsible for a transition from 2 to 1 and responsible for another photon of same energy. Both the photons are in same direction, moving in same direction, they have same energy, they have a fixed phase relationship. So you will get one photon will convert into 2, 2 will convert into 4, and then you will get amplified laser beam. So this is your stimulated emission. Now the next topic which I am going to discuss here, that is principle of laser action. And the term which I have mentioned over here, that term is population inversion. Actually, population inversion is the principle of laser action. And the point that how stimulated absorption and spontaneous emission are equally involved in amplification of light, you can understand now. So what I have shown in these two graphs, you have total n number of atoms distributed in two states, 1 and 2. Let E1 is the energy of state 1, E2 is the energy of state 2, N1 is representing the population of state 1 and N2 is representing the population of state 2. So as I have already mentioned that in normal condition, the population of any energy state that can be expressed through this mathematical expression, n equals to n naught. N is the population of any energy level, n naught is the total population, e raised to power minus capital E is representing the energy of that level which we are discussing, k is representing the Boltzmann constant, and T is the temperature at which you are defining the population. So as you can see from this mathematical expression, in normal condition, at any temperature T, lesser the energy, greater will be the population. So lesser the energy, E1 is lesser than E2. So for state 1, which has energy E1, population is very, very high. Whereas state 2, which is having greater energy, the population is comparatively very low as compared to this particular state 1. This is the normal population. But as I have mentioned that in case of laser stimulated emission process, this process is basically involved in light amplification. And as you have seen in your previous slide, that's for stimulated emission, what you require? You require some electrons in high energy level. So for stimulated emission, if you have electrons in high energy level, only then through a trigger, through these photons, you can trigger a transition from 2 to 1 and you can get additional photons. It means for stimulated emission, the first requirement is that we should have large number of, we should have electrons, sufficient number of electrons in high energy level. If you are having sufficient population of electrons in high energy level, only then you can send those electrons to ground state, only then you can amplify light. So the first and essential requirement to get stimulated emission is that we should have a sufficient number of electrons or atoms or ions or molecules in high energy level. But you know, according to Maxwell-Boltzmann distribution, the high energy level that is having comparatively lesser population. But for stimulated emission, you require greater population. It means this normal population that cannot amplify light, that cannot exceed the probability of getting stimulated emission. So what you have to do? Somehow you have to invert the population. Means somehow you have to invert this normal condition. So this is the condition, this is the state which you have to achieve in order to get amplified laser beam. Means you have to exceed the population of high energy level as compared to ground state. So once you achieve that state, that particular state is known as population inversion state. So I hope the meaning of population inversion is clear now. Normal population is you have greater population in ground state. Inverted population means you require inverted population means greater population in high energy state as compared to ground state. And why you require that inverted population? You require that inverted population state because you want to exceed the probability of stimulated emission, and that can be increased just by increasing the population of high energy level. So this population inversion, these two diagrams completely explain that what is population inversion. Right? So in normal condition, if you have two states, 1 and 2, 1 is the ground state, then 1 is most populated, whereas 2 is having very small population. But in order to get laser beam, what you need? You require greater population in high energy level, so as compared to ground state. So that is known as population inversion state. Now the question arises that how you will increase the population in high energy level as compared to ground state. So the answer of that question is, you are not going to add extra electrons from any external agency. You have to redistribute those electrons which are present in 1 and 2. So for that, redistribution means somehow you have to pump these ground state, the population of ground state to high energy state, so that you can get greater population in 2 as compared to 1. So that particular that particular process, that particular method through which you can get greater population in high energy state as compared to ground state, that method, that process is known as pumping process. So what you need for laser? You need stimulated emission, and to get stimulated emission, you need a large population in high energy state. In order to get that large population, you have to invert the normal population, and in order to get that population inversion, you need a pumping source. So pumping source is that method, is that process through which population inversion is achieved. So this is the entire principle of laser action, right? So you can understand through this animated diagram that what is the meaning of population inversion. Initially, the population of ground state is much higher, but you know, for stimulated emission, greater population is required in high energy level. So you are not introducing electrons from outside or from any external agency. You have to pump these ground state electrons from ground state to excited state, so that you can get greater population in these high energy levels as compared to ground state. So that is the meaning of population inversion. Now, what is the meaning of metastable states in laser system? So the meaning of metastable states is, suppose you have only 2 states, 1 and 2. So 1 is the ground state with maximum population and most stable. 2 is the excited state, that is having a very small lifetime of 10 raised to power minus 8 seconds. Now you have these 2 states, and suppose you are having a pumping source, and through that pumping source you are exceeding the population of high energy level. But you know, in high energy level, since it is highly unstable, electrons cannot stay there for a longer duration. You are continuously pumping from from ground to excited, but in excited they are not staying for a longer duration. So you are not able to get population inversion. Population inversion means these electrons, they have to stay here for a longer duration, but since its lifetime is very small, you cannot achieve that. Means if there are only 2 states, ground and excited, you can never achieve population inversion. So you have to introduce an intermediate state. There should be some intermediate states there where electrons can stay for a longer duration, so that population inversion state can be achieved. So the states, the intermediate states which are there between ground and excited states, which are responsible for population inversion, those intermediate states which are having greater lifetime as compared to excited states, those intermediate states are basically the metastable states in a laser system. And these metastable states which are there between ground and excited state, their lifetime is approximately of the order of 10 raised to power minus 6 to 10 raised to power minus 3 seconds, which is much greater than the lifetime of excited state. So what will happen? From ground state, electrons population will be pumped to excited state. From excited state, since its lifetime is very small, continuously they will keep on coming down to a more stable state, which is actually your intermediate or metastable state there. So the population of metastable state will grow and the population of ground state will decrease, because continuously that population of ground state is pumped to excited state. So then you can achieve population inversion between metastable state and ground state. So that is the significance of metastable states in a laser system. So this is the diagrammatical representation of metastable states. Ground state, most stable. Excited state, roughly of the order of 10 raised to power minus 7 to 10 raised to power minus 8 seconds. Then this particular state, which is your intermediate or metastable state, it is having a longer lifetime as compared to excited one. So from ground pumped to excited, from excited they are coming down to metastable state, then they are staying there for a longer time. So now you have greater population in metastable state as compared to ground state. So these two are now participating in light amplification. So these are metastable states. Now the last one, main components of laser. So the three essential components of any laser system, without which a laser cannot work, without which the amplification in laser is not possible, those components are, the first one is this active medium, or you can say laser material. So active medium is the first important part. Active medium is actually assembly of electrons, atoms, ions or molecules where the light will get amplified. So that assembly, that is known as active medium. And in laser, this active medium or laser material, that can be in any form, in solid form, liquid form or in gaseous form. So all the three states, that is solid, liquid or gas, are possible, and depending upon the state of that active medium, you can classify your lasers like solid state lasers, liquid laser or gaseous laser. So the first essential component is your active medium or laser material. So now you have an active medium, but you know, in order to get light, laser light, you need stimulated emission, and for stimulated emission you need population inversion, and for population inversion you need a pumping source. So the second essential component is actually this pumping source, or you can say the energy source, which will pump the ground state electrons, atoms, ions or molecule to high energy state. So that is the second essential component. And the third one, that is actually a combination of two mirrors. So two mirrors, they are kept at two ends of active medium, and the characteristic of these two mirrors, that one of the two mirrors is highly reflecting, or you can say 100% reflecting, and the other one is partially reflecting. So now what is the role of these two mirrors here? Actually, for stimulated emission, you know, you require an external trigger in terms of photons of energy E2 minus E1, and that external trigger or those photons are not coming from outside. Those photons are actually obtained due to spontaneous emission. So you have to capture these photons within the active medium so that they can participate in light amplification. So in order to capture those photons within active medium, these two mirrors are kept at two ends of active medium. And one more point, that why one mirror is partially reflecting. This end is partially reflecting because when the beam will get sufficiently amplified, the laser beam or laser light that is obtained from this partially reflecting end. So this combination is known as resonant cavity. So three component, first one is active medium, then you have pumping source, and then you have resonant cavity. So from this animated diagram you can understand in these ground, this black one is representing the ground state, these green one representing the excited state, and these red lines are actually the photons. So initially most of them are present in ground state, then through pumping source pump to high energy state, then the population in excited state will grow, then you will get photon due to spontaneous emission, then these photons will participate in stimulated emission, then you will get amplified laser beam. The number of these red lines or these photons will go on increasing, and when they will become very high, then laser light is obtained from partially reflecting end. So this is a working of a laser system. So I have mentioned, I had discussed about all the three components: active medium, collection of atoms, ions or molecules where you will get where you will amplify light; pumping source through which you will get population inversion; optical resonator, combination of two mirrors which are used to capture the photons within active medium. One of the mirror is fully reflecting and other one is partially reflecting. So these were the basic concepts of laser, and the reference books which you can take for this particular topic are given in this slide. So that's all for today. Thank you so much.